All right, for this lesson, we're going to be talking about how to simplify radicals. It's just a skill that you need to know going into obviously this unit and the next unit. So we're going to kind of review that. So first thing we want to do is we want to talk about perfect squares for square roots. So when you're looking at your square roots, you need to write down all of those perfect squares. Now, I will say that eventually you will hopefully memorize these or have already memorized them. So you won't necessarily need to write them down or have at least something to reference. But just so we know, so if I do 1 squared, that came from equaling 1. So if we take the square root. If we do 2 squared, that's 4. So if we take the square root of 4, then that's going to be 2. We have 3 squared. 3 squared is 9, so the square root of 9 is 3. 4 squared is 16, so the square root of 16 is 4. 5 squared is 25, and we're going to take the square root of 25 and get 5. Then we got 6 squared, that's 36. So if we take the square root of 36, that's 6. 7 squared is 49. And then we have 8 squared is 64. And then we have 9 squared, which is 81. 10 squared is 100. 11 squared is 121. And 12 squared is going to be 144. Now, these are important because it's going to be a lot easier to break down a square root if you know your perfect squares when you're breaking down the numbers. So, when I go to simplify a square root, there's lots of options. You've probably done something before where you do like the factor tree and you say, okay, like this is 2 and 10, and then this is 2 and 5. Now, if you don't see an index, so the number inside of the square root, just so we're clear, this number inside of the square root is called the index. That tells me the root number. Then we have the radical itself, and then what's inside is called the radicand. Okay, so that's what we're taking the root of. So what I want you to recognize is that this is a square root because whenever we don't see the root, it's automatically a 2. And what I want you to do is I want you to look for perfect squares. So when I think about taking down 20, I'm always going to look for, okay, what's the highest perfect square number that I can take out of 20? Well, I know the first perfect square is 1. The next perfect square is 4, so 4 is an option. The next perfect square is 9, and then we go to 16, so then we're getting out of our range. So our first perfect square is going to be the square root of 4 and the square root of 5. Now, the reason I break those up that way is because we know that those two are being multiplied together. Now, we're going to talk about multiplication a little bit, but whenever you multiply radicals, you multiply the radicand that's in the inside of it. So I know that the square root of 4 is equal to 2, and then we can't take the square root of 5, so we leave it as 2 square roots of 5. And you can always check yourself when you are looking at these problems. So kind of compare the decimal. So we have 4.47 for the square root of 20, and then 4.47 for 2 square roots of 5. So they are equivalent to each other. We just simplified. All right, so for the next one, we have 32. So again, we have our perfect squares. So we want to think about what two numbers can we break this down into. And we always want to look for our perfect square and our largest perfect square. So when we look at 32, obviously 32 is going to be divisible by 4. Okay, so it's not divisible by 9, but it is going to be divisible by 16. So if I come over here and I just, I need to look at some of the numbers. So we have 9's not going to work. We have 16. So 16 will work, and that we know that's going to break down into 2. So my largest number that I can take out that's a perfect square is the square root of 16. Okay, so we're going to break that down, and we know that the square root of 16 is 4. And then we can't break down square root of 2, so we leave that there. So it's 4 square roots of 2. All right, then we have 125. Now, obviously 125, being that it ends with a 5, it's going to somewhere, probably most likely go into the realm of the square root of 5. So if I have 125, we know that 25 is that perfect square number, which it does divide into that, and I don't think, or we're not going to be able to divide it any higher. So if we break down the square root of 25, the largest perfect square that I can break that down into is 25. So we have the square root of 25 times the square root of 5. So we know this is 5, and we can't do anything else to break down the square root of 5, so we leave it that way. So that's going to be 5 square roots of 5. Now, for this one, I have a number already in front. That's the number that's being multiplied. So technically, this is 3 times the square root of 225. Now, not 225, 252, sorry. So when I'm looking at this, whenever I break this down, I've got to make sure that I include that 3 once I reduce that down. All right, so let's look back and let's look at some perfect squares that we can potentially break this down into. So obviously, with it being a bigger number, it's probably going to be a larger perfect square number. And again, if you need to test this out, you are more than welcome to. So I'm going to just kind of start at 16. So 16 wasn't right. So the next one was 25. And so then the next one's going to be 36. So 36 did work. We got 49. That's not going to work. Then we got 64. So then we're kind of getting out of that range of being able to divide. So 152 is going to be divisible by 36. And it gives me a prime number as my other piece. So really that should have been my indicator that I can't break this down any higher with the square root. So we have and again, this is going to be 3 times that. Okay, so the square root of 36 is going to be 6. So that's 3 times 6 now, times the square root of 7. So if I put this all together, this is going to be 18, because we're going to put that 3 and 6 together, because we're going to multiply those together now that we've simplified that. And that's going to be the square root of 7. So 18 square roots of 7. Now, with cube roots, again, we're going to write down all of our perfect cubes. Now, these may not be as memorized in your brain as the squares, but again, we're kind of going to work with the basics of 1 through 5. There are more, obviously, but if I have 1 cubed equals 1, so the cube root of 1 is 1. So then I have 2 to the third power, and 2 to the third power means 2 times 2 times 2, which is going to be 8. So if we take the cube root of 8, that equals 2. Then we have 3 cubed, so 3 times 3 is 9, 9 times 3 is 27, so the cube root of 27 is 3. Then we have 4 cubed, so 4 times 4 is 16, and then 16 times 4 is going to be 64, so the cube root of 64 is equal to 4. All right, so then we have the last one on this list, but again, there's more. We have 5 cubed, so 5 times 5 is 25. 25 times 5 is going to be 125. So these are our first few perfect cubes that we can look for. And we're going to do the exact same process. We're going to find the largest perfect cube to break these down. So if you notice in these, I have the index is a 3 this time. So they actually are writing the 3 and it's smaller. That's very different than if I have a 3 on the outside that's being multiplied versus the 3 that's kind of in this check mark right here. So when we break this down, we want to look for our perfect cubes. So we want to look for our largest perfect cubes. So we got 1, 8, 27, 64, and 125. So if we think about 8, and we say 40 divided by 8, that's going to be our largest perfect cube. So we're going to say the cube root of 8 times the cube root of 5. So we can break the cube root down as a perfect cube, and that's going to give me 2. So this is going to be 2 cube roots of 5. And we're going to leave that just like we did previously, because that can't be broken down, and it's going to wind up being an irrational number. All right, so we got 162. So we got 1, 8, 27, 64, and so forth. So when we think about 162, we want to be able to break that down with our highest perfect cube. So the first one that we had obviously was 1. Then the next one we had was 8. So 8 didn't work. We got 27, so there's 27 and 6. So 6 is not a perfect cube, and we're not going to be able to break that down further, so that's going to be my highest. So we're going to say that we're going to be taking the cube root of 27 times the cube root of 6. So the cube root of 27 is going to give me 3. And we're left with the cube root of 6 that is not going to be broken down any further or simplified. So we have 3 cube roots of 6. All right, same thing with 192. So 192, I'm going to start with 27 this time. That didn't work. So then the next one that we had was 64. All right, so 64 is definitely going to work, and that leaves me with 3. And that cannot be cubed any further. So we're going to use 64 as our largest perfect cubed. All right, so when we break down 3 cube roots of 64, that's going to be 4. And we're left with times 3 roots of 3. And again, just like the other one, I have this number out front. So this number out front means that I'm going to multiply. So my index is still 3, and we're going to multiply our answer by 5. So 56. So we have our basic, which is 8. So 8 is going to be our largest just because it can't go any further than 7. So we're going to bring down that 5. We're going to say times the cube root of 8. And then the cube root of 7. So the cube root of 8 is 2, so that 2 is going to be simplified with the 5 in front. And then we have the cube root of 7. So if we put this all together, we're going to say 5 times 2 is 10 times the cube root of 7. All right, so let's talk about a little bit of multiplying radicals. So when you multiply the radicals, you multiply the radicand first. So what do we mean by the radicand? Remember, the radicand is the number on the inside, and then we simplify. So when I'm looking at these problems, we're going to multiply the 2 and the 3 together. Now, these have to match as indexes, so the indexes have to match. So index must match. Okay, that's very important. These are both square roots because we don't see them. So if we multiply those together, we get the square root of 6. Now 6, there's no way to break 6 down any further with a perfect square, so that's going to stay the same. All right, so for this one, we're going to multiply 12 and 10 together. So this is going to be 220. All right, so we're going to do the square root of 220. Again, we need to look for a perfect square this time. So 220, and remember our perfect squares, just to kind of go back and look at that list, are over here. So we're going to start, and we're going to look for which one is our largest. So we're going to say divided by 4. Obviously 4 works, but we may have something a little bit larger. The next one would be 9, so 9 doesn't work. 16, so 25. All right, that's not going to work. We had 36. And then we can see that when we break this down, I think the one we had was 4. So looking at this, 55, we can only break 55 into what? 5 and 11. So technically 4 would be our largest after kind of going through that process. So we're going to break this down, and we're going to say the square root of 4 times the square root of 55. That's going to be 2 square roots of 55. Now again, we have our indexes. They do match, so we're doing cube roots this time, and we have a 6 out front. So this is going to be 6 cube roots, and then we're going to multiply 40 and 375. So 40 times 375. And you could essentially break them down individually first, because it is going to wind up being a huge number, and that's okay. I mean, we can kind of work our way through the process. So we got 15,000. All right, so we obviously need a pretty big number here. And all right, so we're looking at the cube root here, and we're trying to find that largest cube root. So of course we're going to just kind of investigate. So the largest cube root that we talked about was 125. Especially with it being that odd number. So 125 definitely didn't work, but we do have 120 left over. So 120 could potentially be divided a little further. So let's see if there's anything higher. So we did 5 cubed, and that got us 120. Let's do 6 cubed. So that's not going to work. 7, 8, 9, 10. Oh, so 10 does work. So I think we need to go with 10 cubed. So yes, you may have to kind of play around with it a little bit, especially that we didn't get a higher cube number. But 10 cubed is going to work for this situation. And again, use your calculator to kind of investigate. So we're going to do the cube root of, and 10 was 1,000. And then we had, once we divided it by that 1,000, we had 15 left over. Okay. So that's going to be 6 times 10 times the cube root of 15. Now 15, we don't have any cube roots. They're going to break that down any further. So we multiply that together. All right, so we multiply the 6 and the 10 together. We get 60, and that's going to be times the cube root of 15. And again, we can check that in Desmos. I already put the problem in there. But we can put 60, and then we're going to go select the cube root function. It's under functions. Scroll way down until you see where it has n as the index. And then you're going to put in 15, and we can see that that does, in fact, match up. All right, so once we do dividing, so to divide a radical, the first thing you're going to do is you're going to separate the numerator and the denominator. Okay, so just as a quick overview, so if we separate these, that's going to be the square root of 9 divided by the square root of 16. And for right now, we're just going to be working with those perfect squares. So we know the square root of 9 is a perfect square, so that's going to be 3. Square root of 16 is 4. Same thing with this one. We're going to separate the numerator and the denominator into different radicals. So this is the square root of 121 is 11. Square root of 64 is going to be 8. And then finally, we have the square root of 225 divided by the square root of 9. Now, 225 is a perfect square for 15, and the square root of 9 is going to be 3. So if we do simplify that, we can actually divide that out. So that's going to be 5. All right, so with these last ones, we're going to be looking at the same types of problems. We're going to add in the variables, okay? So when I'm looking at variables, we're still going to be looking at how many there are. So just as a reminder, if I say I have x to the third power, that means that I have x times x times x. So that's how many I have for each variable. So we're going to start with the number itself, and we should see that 25 is a perfect square, so that's going to be 5. So if I take the square root of 25, that is going to be a perfect square of 5. Now, this is an index of 2. Now, an index of 2 means I need to be able to group pairs. So for this one, I have x times x, and then I have y times y times y. So I can group these x's in a pair and my y's in 2 pairs. So without having to write this out every time, I simply can say divided by, because divided by puts stuff in groups, the index number. So if I say 2 divided by 2, that's going to be just x to the first. And if I say 4 divided by 2, that's going to be y to the second, which means we had 2 groups of those. So in this situation, we're going to break 18 down. Our largest square root is going to be 9, and square roots of 2. And then in this one I can divide by 2, because this is an index of 2, but this one has 3. So the way to handle an odd exponent is to drop it down to the even. So we're going to say b squared times b, and then we divide that by 2. Okay? So with that being said, I know that I am going to have a b by itself. Actually, let me write this out. So we're going to take the square root of a squared and the square root of b cubed. Okay? So in this situation, I have 3. The square root of 9 is going to give me 3. So we're left with the square root of 2. A squared, we divided that, so we're just going to have 1a left over. And for this one, remember we dropped this down. And we said, okay, we're going to make it in the next even situation, so we divide that. So that's going to be left with b on the outside and a b on the inside. So if I put this all back together, okay, because again, this is technically a times a, and this is b times b times b. So I have a group of a's, so that's the reason I only had 1a left over. And then I had a group of b's, and there technically was one left inside the radical. So I'm going to multiply the 3, the a, and the b back together in front. So that's going to be 3ab. And then on the inside, we're going to multiply the 2 and the b back together. So that's going to be the square roots of 2b. All right, so now we're going to be looking at groups of 3, okay? So groups of 3 because it has an index of 3. So our first perfect cube root, or cube root that we're looking for, and again, remember these are perfect cubes. We got 1, 27, 1, 8, 27, 64. So with 81, if I divide that by 8, that's not going to work. If I divide it by 27, that gives me 3. So we know we can break it down into 3. So we're going to do the cube root of 27 and then the cube root of 3. Now, essentially what we're doing is we're going to say the cube root of 5 and the cube root of n. Now, when I'm looking at this, I need to be able to group it into 3. So the only way that I can divide 3 into 5, that means that I would have 3 times 3 times, or not 3, sorry, m times m times m times m. So I would only be able to make one group of 3 because there would be 2 left over. So I can take an m out when I take the cube root of that, but I'm left with 2 left over. So if I put this together, so the square root of 27, that's 3 times the cube root of 3. Now, this one I'm going to pull, it's going to reduce to an m on the outside, and then I'm going to have the cube root of m squared because there was 2 left. Now, I can't take any n's out, so I'm left with the cube root of n. Okay, so I'm going to multiply all the things together. So we have m and 3. And then on the inside, I have left over 3m squared times n. All right, so we're back to square root. So 25, my largest number that I can divide out of those is going to be 25. That's a perfect square, and 5. Now, these two are even. So I know that because these are even, I can divide those by 2 and this one by 2. But this one is just a 1, so I can't group those. So those are going to have some left over. So this is going to be the square root of a to the 4th, the square root of b squared, and then the square root of c. So this is going to be 5. We're going to have the square root of 5 left over. A to the 4th, that means I'm going to have 2 of them, so that's going to be a squared. B divided by 2 is 1, so that's times b. And then we're left with the square root of c. So we're going to multiply the 5, the a squared, and the b in the front. And then we're left with 5 on the inside of the radical and c. All right, and then cube root again. So we know that 8 is a perfect cube root, so I don't even have to adjust there. So 2. I should be able to say, okay, there's no way I can get a group of 2x's out. There's no way to do that. So that's going to be left. So then we have the cube root of y to the 5th. Well, technically I can take one group of 3y's out and reduce that. Okay. And then for my z's, I have one group of those. And I'll have no z's left. So when I simplify this, this is going to be 2. The x's, that's going to reduce down, or that's going to stay the same because we could not do anything with that with the groups of 3 with the root of 3. Oh, and I did forget my z's over here. So z is the cube root of z cubed. So this one, we're going to wind up taking one group out of y. So there's 1 on the outside, but we're left with 2 on the inside. So that's going to be the cube root of y squared. And then we're able to reduce all the z's out of the cube root. So if I put this all together, that's going to be 2yz on the outside times the cube root of x squared, y squared, and z. Please let me know if you have any questions about this, and I'll be more than happy to help.